No lab tomorrow, right?
Right.
No class on Monday, right?
Right.
No lab on Monday, of course. No lab on Tuesday because there's no lab on Monday. Literature assignment I gave to you. I've been thinking about due dates for things. The due date for the lab you're doing yesterday and today, that's a report. It'll be due when you come to lab next week on Wednesday or Thursday. The day you come to lab. The literature assignment will be due on Friday in class.
Next week.
Next week, next Friday in class. Okay? Other questions before we get going? Yes?
So on the daily question, I tried to do number 2, where you had to write the 2 glue structures.
You doing homework?
Yes.
All right. What number?
That was surprising. Number 2?
Those structures?
Yeah. Yeah, because I got 8 DUS when I did the math, and then when I tried to do the structure, I couldn't get the proper number of DUS.
Well, when you do structure, that's up to you. So you want to just do a structure to make sure you have, how many DUS in the formula?
8.
8, is that right?
Yeah, that's what I got.
Let's see here.
Divided by
This is not
Yes.
not good.
Okay,
Analogy
yeah.
only makes one bond. You want to show all bonds, all on pairs.
Because I choose after I kind of gave up on it. I looked at stuff on Google, and there's like a whole bunch of the formulas that people had.
No, you're not going to find anything on Google, and you want to do it on your own anyway, because you're not going to have open Google when you take the test. We did one like this in the lab, sort of lab lecture, or a little bit during lab. Use functional groups, DUS, and then put up some functional groups. You got 8 carbons. What function? What can you throw up real quick? How many DUS? Okay, so benzene ring. I mean, that's a ubiquitous.
Well, not benzene, but.
A substituted benzene ring. So, I mean, you can throw up a benzene ring. Right there, you got 6 carbons and 4 DUS. I'm not sure it's 8 DUS.
No, it should be 2, but like a ring, just not the double bonds.
How many DUS in the compound?
I think there's a little bit.
Two.
Yeah, I forgot
don't-
to
it
subtract
doesn't
the
look like
14.
8.
I forgot to subtract the 14 from it. Yeah, you're right.
Yeah, it doesn't look like 8. Too many hydrogens. That 2 and plus 2 is 16, 18 is 2. Since there's only 2 DUS, you can't have a benzene ring. So that's 4 DUS right there. But you could have a cyclohexane, saturated, more saturated ring. And then you could have 2 more carbons. We got 2 DUS, 2 more carbons. Well, let's make that an alkene then, coming off. That's 8 carbons, yeah. Chlorine. We can just tag a chlorine on here. Essentially, we're replacing an H with a chlorine. Nitrogen. Problem is if we... Now we can do this. We can just tag on a nitrogen. And you're going to have to put H's here. Like 2 H's on the nitrogen. I want to do it like this, but if we're doing an official Lewis structure, probably want to draw out the H's. H, H, lone pair, 3 lone pairs. And then an oxygen, 2 oxygens. Problem is, I can't have any more double bonds because I've already got my T DUS. So these are all going to have to be single bonded with H's. Maybe put oxygens like this. And that's a pretty decorated ring right there. I like some substituents coming off of that ring. Do we have the right formula? 6, 7, 8. chlorine, nitrogen, 2 oxygens. And I guarantee you the H's are right because the DUS is right. 14 H's. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, that one does not contain an ester. They ask you to do one with an ester. So I would just start with the ester, all right? Which was on the, yeah, I mean, and then you want to put something here to make it an ester, and then you keep building, you got to have one more DUS, but the 2 oxygens are in your ester. All right? So, try that one. Yeah, questions? There's a million different, I don't know if it's a million, but there's a large number of different structures you can draw for that formula. All constitutional isomers. You could also probably draw some stereoisomers, but we haven't got there yet. Okay, good. Next one was solubility. How do we do on that? This is Cipro, an antibiotic called fluoroquinolone. Would this compound be more soluble or less soluble than Cipro? In what? We've got to say in what? In water, okay. More or less soluble?
Less.
Why less?
There's more hydrophobic rings.
The only difference is, this is 3-membered cyclopropyl, this is what, a cycloheptyl, 7-membered ring? That's going to make it more or less soluble in water? Less. It's more hydrocarbon, non-polar hydrocarbon. Don't like water. Hydrocarbon's hydrophobic. Should be less. What about the one on the right?
Less.
What's the difference?
There's less hydrogen bonds.
This H is replaced with an ethyl group. More hydrocarbon, less soluble. We're also removing hydrogen bonding potential when we remove that H, which is a hydrogen bond donor. Now, both of those on the right are going to be less soluble in water than Cipro itself. What if we replace the fluorine with an OH?
More.
Be more, because now you got, well, this can hydrogen bond, although there's a debate, but can an aromatic fluorine really hydrogen bond? For us, it should, but in actuality, it's a little vague. Okay, so you could modify Cipro to do what you want, make it more water soluble, less water soluble, et cetera, et cetera. You understand physical properties and your functional groups, and hydrogen bonding, and IMFs, et cetera, et cetera. That's what we're doing here. Reaction of this with HBr. Oh, acid base. Let's pick up on acid base. Then we may look back at the pink handout for properties. At the end of that, okay, inductive effects through single bonds, pushing and pulling, based on electronegativity. Inductive effect. And sp3 carbon does what? What by induction? sp3 carbon does what? Donates by induction. Okay? Something you just have to know because it's not really much electronegativity difference there, but okay. The reason why is it can be explained, but it's a touch above what we're able to do right now. sp3 carbon donates. Seems like we left off about right here, yeah? Where did we leave off at? We did this one here,
Yes.
not here.
Yep.
Which one's more acidic? They're both alcohols. I hope you understand we're talking about the OH because CHs are much less acidic. Which OH is more acidic? Well, this one's branched, this one's linear. When you have branching like this, first off, this out here is just plain sp3 carbon. First off, we're considering the anions, right? And we want to say which one's most stable. All right, this has this hydrocarbon chain which donates sp3 carbons. If it's one long chain, it's like one donation. When it's branched like this, these sp3 carbons, it's like there's 3. And all of this donation comes into this and pushes into this area here. And is that going to stabilize the minus or hurt it?
Hurt it.
It's going to hurt it. You don't stabilize minuses by pushing electrons towards it. You stabilize minuses by pulling electrons away. That hurts it. So it's going to make it less likely to form. So the original OH compound is less likely to act as an acid. This original compound is more acidic. We ended yesterday with asking this question. Which anion, oxygen anion, is most basic? Which one would want an H the most? On the right, the one that's least stable. It's like, hey, I got too much minus because I got these 3 rich friends donating money. You know, sometimes you got too much money, right? All right? It's like I got to... all right, which is more acidic down here? The difference? Okay. Well, we're talking about the OH because CHs aren't that acidic. You'd rather make it O minus. But which O minus is going to be best?
But the chlorine's a lot bigger. The chlorine's a lot bigger.
The what is bigger?
The chlorine.
Does it not make a difference if it's so?
Yeah, the chlorine is bigger because it's lower. But what did we say yesterday? And I told you that I have to remind you that is the charge on the chlorine? But it don't matter.
So
It only matters when the charge is on the atom. And you say it's bigger, the charge is more spread out. Charge ain't on the chlorine. The size doesn't matter. The only thing going on here is withdrawing. The fluorine is on the end of the rope here. Good tug of war, pulling inductively through these single bonds. The effect is here. I pull here and I affect you way over there because I'm pulling through all these single bonds. Yes, the chlorine is pulling, but it doesn't pull as much. Fluorine pulls more. It's more electronegative. So which anion is going to be more stable? This one. Thus, the original OH compound is more willing to serve as an acid and become an anion here. That one's most acidic. Size only matters when the charge is on the atom. Which is more acidic down here? What's the difference? Now, if you think about tug of war, it doesn't matter how long the rope is, I'm still going to affect. Like a train or something. If I'm pulling, it don't matter how far over there, it's going to be affected. That doesn't exactly apply here. The effect actually tails off. The further away this is from where the anion is going to be formed, the effect does diminish as you get away. Right. So which one's more stable? Well, the left. Fluorine's closer. As the fluorine gets away, the inductive withdrawal of the electronegative fluorine is not felt as much over there. So the original, I'm circling the original acids that are more acidic. They're more acidic because they're forming a more stable anion. We had something like this compared to one of these. 3 fluorines pulling.
Is
thought we said the left one was most acidic.
Okay, yes.
Okay.
And both of these last two, these are both more acidic. Yes. Yes. Sorry. Have something like this with 3 fluorines, both pulling. That's sort of the opposite of like this. These are 3 donating, and these are 3 pulling when it's sort of branched like this. So this original OH compound would be more acidic than both of these. Fluorine's 2 carbons away. Okay, that has 1 fluorine on that carbon, this one has 3. So this anion would be more stable. This OH compound would be more acidic. I show that because it's very common to have 3 halogens on 1 carbon. Okay? Not super common, but you do see that a good bit. Sometimes even more than just having 1 halogen. Okay, so now number 3. What was number 2? Okay? Well, my handouts have headings that should be very meaningful. Organization. If you don't know what number 2 is, you're missing the whole point of the previous page. What's number 3? Resonance effect. Okay, look at these 2 OH compounds. That's an alcohol. This is a what? Carboxylic acid, which is more acidic. One's called alcohol, one's called an acid. Carboxylic acid. But why? Well, we want to look at the conjugate bases and ask which is more stable. Well, what can we discuss here? The architecture of this anion. Any properties that we're able to discuss? I see this sp3 carbon chain. What does it do?
Pushes electrons.
Inductively donates. I'm showing that with some donation here by dipole arrow. Pushing electrons here. How about over here? Well, you got an sp3 carbon that donates as well. But now you got this oxygen and it pulls. And it's not pulling directly away opposite, but it is pulling, it is considered pulling away from this. Okay? So if you kind of like, it just pulled and turn. Alright? That right there gives you the answer because this has nothing pulling away. This pulling here should make this more stable. That explains why this is more acidic. Again, because this is more willing to give up the H and act as an acid and become the minus. I don't mind becoming minus because I'm going to be stabilized by this guy here pulling. But that's not the main answer here. The main answer here is resonance. Okay? Resonance. Now there's some discussion here. I'm not going to just read it to you. I'm going to give you a Cliff Notes version. Okay? You can read it. Basically, there's a variety of ways I can try to present this. We're early on with our resonance. You got to keep reading. Okay, every little bit you build, and guess what? Then test 3 will cover resonance. Again, most textbooks cover resonance in chapter 1, 2, or something. I think it's too much. Bits and pieces here along the way. Okay. We can start with this right here that's very important that we should know already. It's a hybridization of this oxygen here. Whenever you do hybridization, charge is meaningless. Just ignore the charge. It affects nothing. What's the hybridization of that oxygen? Somebody said 3. It's sp2, right? Why is it sp2? What? Because the double bond more precisely. P orbital next door. Yes. P orbital here. Right? This molecule, I'll join the carbon, oxygen. One electron over interaction to make pi bond. You see that pi bond there? And then oxygen has 2 lone pairs. But then over here, this oxygen has some lone pairs. Would a lone pair like to be in a p orbital? Yeah. We put one of these lone pairs in a p orbital. And then the others are going to be in hybrids. You see the trigonal planar? The 3 lines is your trigonal planar. 120 between the lines. P orbital is actually coming out. Okay? That's an sp2. Alright? sp2 with LP in p orbital. Now you're only going to put 1 lone pair in a p orbital. Unless maybe there were 2 p orbitals next door, then you could do something fancy. Okay? Why? Because now this p orbital can interact with that, and you got a p orbital game, which is very, very good. It's called resonance, conjugation. Okay? And this is a stabilizing effect. That's why it's very good. So we've got some resonance going on here. Lone pair conjugated. How about over here? What's the hybridization of that on? This is just sp3. Are we going to put one of these lone pairs in a p orbital? No, there's not one next door. And so you would never put it in a p orbital because a p orbital is actually higher energy than a hybrid. It's okay over there, yes, a p orbital is higher energy than a hybrid, but that's offset by the fact that the p orbital is interacting, so it's actually better. Okay? Now we can kind of say this. We started with 2 lone pairs. When it acted as an acid, it became the anion, it took on another lone pair. Here's sort of the summation of this. The extra lone pair, really any of them, but one of the lone pairs here is stabilized by resonance. And that really stabilizes this thing here, this anion. Where over here, you don't have any stabilization by resonance. The lone pairs are just out here, and they're not doing anything. It's just 3 lone pairs. 3 lone pairs. Over here, one of them is interacting, like, ooh, this is nice. I'm interacting. Yeah, cool. And that interaction is called bonding, but it's pi bonding. It's resonance. This interaction stabilizes you. You got hit here. It's called resonance. Okay? This is resonance stabilized carbanion. The Klein book calls it delocalized. Because it turns out that this anion is really not here. It gets to share through here. And that's discussed here. There's a section in the Klein book about localized lone pairs and delocalized lone pairs. It's resonance. Lone pairs and p orbitals are delocalized. You can read that. That's sort of the take-home to recognize it. And really almost all we need now. Going forward, we'll do resonance structures, especially when we get to test 3. And we'll do a little bit down here. Again, the take-home. If one of the lone pairs is in a p orbital doing that p orbital stuff, it's going to be much stable than if the lone pairs are not doing any of that. And that's the answer up there. The one on the right is more stable. Thus, the acid, the carboxylic acid, is more acidic. By the way, what pKa's are these? You need to start learning pKa's. Not memorizing every one, but by the time you finish with organic 2, you need to know 6 or 8 pKa's. What's pKa of a carboxylic acid? There's a list in the back of your lab manual. About 4, maybe 4 or 5. What's pKa of an alcohol? Same as water. No, much higher than 7. About 16. How much more acidic is the acid? 10 to the 12. What is that, 100 gazillion? The carboxylic acid is 100 gazillion times more acidic than the alcohol. Right? Why? Resonance, because the anion is resonance stabilized. It's so much more willing to be formed. Okay, resonance structures. The delocalization comes from seeing resonance structures. Resonance structures comes from just moving your electrons, no atoms. For example, maybe we can just move these electrons up. Why would you move them up? Well, the oxygen is electronegative. If you just moved them up, you would get to this structure. A polarized resonance structure. But here, you could be like, well, what could we do here? And on day 1, if this needed electrons, didn't we ask these to come in here and share? And that would give what? Pi bond between here? So we can move between these different structures. But guess what? Or let me ask you, which one's the right structure? All of them are the right structure, because once you have resonance, no individual structure is correct. The electrons are able to move all the way through there. And any one structure we draw is no longer adequate. And the true structure is what's called a resonance hybrid. Okay? So, but you don't need to do any of this to get the answer up there. Up there, you have to just recognize that the lone pair is doing something. It's conjugated, it's impure. Okay? Start looking at drawing resonance structures. Okay? All we're there is moving pi electrons, not moving any atoms. And we'll say more along the way. The charge is delocalized though, because here the charge is on this oxygen, just like I showed originally. Is there any minus charge on this oxygen? Actually, yes, and you can see it from this structure. See how the charge is now on that oxygen? Charge is delocalized, because the electrons are able to distribute in there. And some of the electrons here are actually sitting more this way, and a lot of this electron density is actually on this oxygen. And again, the true structure is a blend of that. Like the colors. I'm showing you red and white, but I'm asking you to understand the true structure is pink. It's a blend of red and white. More later. Okay. And you can read that again for the more progressive discussion. Okay, down here. Resonance is very important. It's a great way to stabilize an anion or a cation when we get over to cations. Sometimes resonance can outweigh other effects, or sometimes it actually does. Which is more acidic? This NH compound or this OH compound? Well, I already gave you the answer. Based on pKa's, which is more acidic? This. Does that make sense then? Would the NH be more acidic than the OH? Would you rather form anion on nitrogen or oxygen?
Oxygen.
Oxygen. I mean, that could be an... Why oxygen?
It's more electronegative.
More electronegative. So why is the NH compound more acidic? It's like the anion refers to form of the nitrogen in this case. Why?
Stabilized by the heat.
Well, let's look at the conjugate basis. If you're just looking at electronegativity, say the O minus should be more stable, more electronegative. We can handle minus better. But the pKa's, the reality tells us that this is more stable. Why?
Resonance.
Resonance, what?
I was just saying, because the lone pairs can go up to the p orbitals.
Because you got to recognize that one of these lone pairs is in a p orbital. The other is in a hybrid. Okay, this nitrogen is sp2. Okay, the anion here. And then you got p orbitals here and here, and one on the oxygen. Okay, but they're interacting. It's actually doubly interacting. It's interacting with one on both sides. Is one of these lone pairs in a p orbital? No. This is a delocalized lone pair. One of them is, the other one's localized. It's not doing anything. But over here, all these lone pairs are localized. They're just on the local oxygen. Okay? So this, you got conflicting arguments. More electronegative, but resonance. Which one wins out? Well, here we know because we're given the answer. It actually is pretty significant. It's a difference of what? How much more acidic is cinnabar? 10 to the 8 or 10 to the 6? 10 to the 6 is a million. I mean, it's a million times more acidic, even though it's nitrogen. Because resonance is a huge effect. But also because it's doubly resonance. If there wasn't a p orbital here, if we get rid of that, you would have resonance, but it wouldn't be as acidic as that. Now, you wouldn't be able to tell that because I could give you apples and oranges and okay. It's mainly because it's doubly resonance stabilized. P orbitals on both sides that makes it so much more acidic. Okay. Localized lone pairs versus delocalized resonance conjugated lone pairs. Again, there's a section in Klein about that. Okay, fourth, hybridization effects. Let's look at these CH compounds. Can a CH be acidic? Not often, because you don't want to make a carbanion very often. But there are some CH compounds that have some acidity. Let's look at these CH compounds. And I've underlined the H that we're looking at. The H on the sp alkyne carbon is more acidic than an H on an sp2 alkene carbon. And these are more acidic than just plain hydrocarbon CHs. What makes this H more acidic? Hybridization effect. What do we mean? We want to look at the conjugate bases. The conjugate base of this would be this. I'll go way over here. Conjugate base of, if this acted as an acid, would be this. This is more stable than this. Why? Hybridization effect. What are we talking about? What is the hybridization of this carbon? In particular, this lone pair is in what type of orbital? Again, cover that charge. Charge means nothing to hybridization. How many regions?
2.
Okay, can you graph that carbon there? Graph the hybridization of that carbon. It is sp, 2 hybrids, 2 p orbitals left over. I see what? Sigma bond to carbon. What else do we see? Pi bond to carbon and pi bond to carbon. And what is this all together?
Triple bond.
Triple bond. Where's the lone pair? That's what you'd be, right here. Okay. The lone pair is in an sp orbital. Right there, sp hybrid orbital. What type of orbital is the lone pair over there in? This is sp3. Hopefully you see that, or are you going to look at that? Okay, which lone pair is more stable? sp. Because that orbital, which is, we're talking about electrons, the orbit, okay? Yeah. Lower energy, 50% s. That lone pair is in an orbital that's 50% s, where the one over there is in an orbital that's only 25% s. 50% s. These electrons are going to be more stable. Another way to consider this, these electrons are closer to the nucleus. More s character closer to the nucleus. And nucleus is like mom. Okay, closer to mom. Alright? More stable. Really, they're closer to all those protons in the nucleus. So there's less charge separation, and it leads to more stability. You boil it down to little physics, basic. All right? But that's very important. Hybridization effects are very important. That's what we got here, is a difference in hybridization. They're both carbon, so there's no difference in electronegativity. Neither one of those lone pairs is in a p orbital, so neither one has resonance. What we have here is a hybridization effect. My example was with carbon. You do the same thing with nitrogen, anything, okay? And actually, I didn't give numbers here. The pKa for this is about 25. Where this is more like about 35, and this over here is like greater than 40. So not that acidic. I mean, alcohol was 16, carboxylic acid was 4. Not that acidic. It's more acidic than the other ones, though. And it's acidic enough that we will do a little bit of chemistry with the alkyne CH. Bases. Okay, like I said, bases are your thieves. They take protons. All right? I think in Gen Chem you said they accept protons. Okay? Yes, the thief accepted my bicycle. No, the thief took your bicycle. Right? Bases take H's. Because mechanistically you start with the base and you go take the H. If you want to think mechanistically, that's why I want to get you to think in taking, not sitting back and donating. Because if you, or accepting is like here, accept. Well, guess what? Your arrow's backwards. On the other hand, if you come take the H, then you'll have the right arrow. Mechanism. Okay. Bases. Well, we got good old acid-base reactions here. Well, we can identify the base, etc. in our acid-base mechanism. Okay. You got to be a little careful here. I don't know who did this. Anion. These electrons going to make a bond to the H. These electrons moving on to the oxygen. That's the same thing we did yesterday, our one acid-base mechanism. What does this give? This carbon is now bonding to the H. There it is. That used to be a lone pair. Now it's a bonding pair to the H that it took. These electrons move on to oxygen, become the third lone pair. Lo and behold, we have charges. That's an anion. Now neutral. Now that's an anion. And probably in the back of this handout, I probably gave you some summary statements for acid-base. Free information. Okay, you can thank me later. The itemized list of free information. Probably on there it talks about charges. And you all know this from Gen Chem, right? In any acid-base reaction, you're going to have a charged species that becomes neutral. And a neutral species that becomes charged, right? It's always there. But maybe it's important to just recognize that. It doesn't have to be, because if you're dealing with dianions, it can go from 2- to 1-. And you're like, well, neither one of those is neutral. Yes, that's true. But usually in organic, we don't deal too much with more than +or -1. We rarely have -2 or +2. Okay, pKa's. Bases are often anions. That's why they want an H to go, so they can go to neutral. That's why they want to take an H. They don't have to be anions. For example, here, ammonia is not an anion, it's neutral. It can take an H from water. Same old mechanism. These electrons take the H, these move on to there. What do we get? Now the nitrogen is bonded to a fourth. I showed this condensed, right? But we know that's nitrogen here is now bonded to a fourth hydrogen. Comes from that arrow right there, right? Nitrogen bonded to that fourth H. And this nitrogen is positive, right? So that's what this is. It's just condensed. Weak hydroxide. Here, both of these are neutral and we made 2 ionics. I mean, your charges can be a variety of things. You don't have to memorize anything. You just do your mechanism and then you assess charges. Okay, what's a good base? Something with high electron density. Electrons that want to go take an H. High electron density. Let's use the same principles we were talking about before, but here it's going to be just kind of reversed. High electron density, which is more basic, ammonia or methylamine? Oh, methylamine, we got a carbon there. Well, what's the difference? Obviously the methyl. What does it do?
Pushes electrons.
Yes, it inductively donates. So which nitrogen lone pair is more electron rich? More electrons there other than just 2 dots. On the right. Because this pushes electron density here, all right? This is sort of electron density, but here you got more electron density. And you have to just understand that the electrons are not just all sitting here. This bond here, I can sort of push them towards you, and then your lone pair becomes even sort of more robust, more electron rich. Okay? This donation here, more electron rich. Strongest base, that's a stronger base because of the inductive donation of the methyl group. Since this is more electron rich, it's like more negative. And this H is partial positive, right? Because of this dipole. So the more negative nitrogen is going to be more attracted to the partial positive H. Any acid has a partial positive H. That's why a lot of times we just call it H+. But it's not always, it's never a free H+. There's a partial positive H. Okay, which is more basic? Methylamine or this guy, which we don't know the name of the functional group yet. We'll learn that in organic too. It's a double-bonded nitrogen. What's your argument here?
The other one's more stable because of the p orbital, which would make it more acidic.
What do you mean p orbital?
The lone pair of the nitrogen would want to be in the p orbital range.
No, this lone pair is not in p orbital. Why do you think it would be in a p orbital? There is
I know
a
you're
p
right.
orbital next door, but we tried to clarify that.
Yeah, it's attached.
For example, you're only going to get that funny thing whenever it looks like it's sp3 and becomes sp2. The p orbital next door, yes, there is. But there's a nitrogen p orbital, and that's that pi bond. If we put this in a p orbital, we could do that. Make another p orbital on nitrogen for that long. It would have to be like this. And if it's like that, well, there ain't one next door. Because the one next door is like this. So really, we could say there ain't one next door. And if you graph the hybridization, that's a standard nitrogen. It's sp2. This nitrogen is sp2. I see, what type of bonds do I see? Sigma bond to H, sigma bond to carbon, pi bond to carbon. And the lone pair must thus be where? The lone pair is in the sp2. The p orbital is being used to make the pi bond. This lone pair is in what type of orbital? sp3. There's your difference. That's a hybridization. Which one's going to be more basic?
Go all the way.
The sp3. Why?
Well, the closer, the more S character you have with acid, or it would be more acidic if it has more S character. So that one has less.
No, not more acidic.
But more stable, I guess.
I mean, that, no, the nitrogens aren't acidic.
Well, I'm just going back to terms of like hybridization.
Yeah, it's hybridization effect. On the right, the lone pair is closer to mom.
More S, right?
More S character. The lone pair is held tighter to the nucleus. Here's the one on the right. The lone pair is held tight because it's more S character. Here's the proton, okay? Nitrogen over here, electrons are out here. All right? Electrons out here are going to be able to do stuff. They're more free. All right? And I can say this nitrogen's a better parent. It holds its electrons tighter. The other nitrogen lets its electrons get out there and react with protons. Okay? Good parent, bad parent. More basic. Down here, which is more basic? Usually we want to identify what type of orbital the lone pair is in. But the lone pair is what acts as the base. This lone pair is what type of orbital? Already said there, right? This one? That one?
And that one is, that one's in P, isn't it?
Yes, that was in a p orbital. Because there's a p orbital next door. And there's no p orbital here. One next door, nothing over here. Well, let's put the lone pair, and now we can line up. In the previous one, we already had a p orbital here lining up. And then you're like, well, here's the lone pair. Well, tough. We're not going to break the pi bond and make it line up. We couldn't do that over there. Here's our classical exceptions. In p orbital, conjugated, delocalized lone pair. Which is going to be more basic?
The first one.
On the left, the summary here is this lone pair is busy doing something. This lone pair is stabilized. It's busy conjugating. It's not interested in a proton. It's got some bonding stabilization already going on. Over here, though, that lone pair is just here. I need something to do. I'll go bond with a proton. More basic. Lone pairs that are in p orbitals typically not basic. They're busy conjugating. They're satisfied. They're happy. Yeah. Which is more basic, F minus or Cl minus?
F minus.
Yeah, F minus is
Legend? Layla? Jay?
Yes.
Which is more basic?
It would,
Asia?
Would it be
Chlorine?
before?
I can't quite hear.
So you would, yeah, the CO.
What's your argument?
Because
Well, so which one's more electronegative? Okay. So because it's more electronegative, what? More what?
That would make that a better acid.
No, these are not acids. There's not even a proton here. So I mean, these are not acids. I thought your argument was going to be this is more electronegative, this is more stable.
Yeah.
Since it's more stable, it's not interested in H. I'm stable, I'm happy, I'm just going to sit here on the couch. But it's not more stable. That's actually more stable. Why?
it's a lot bigger.
Oh, it's bigger. Charge is on the chlorine, it's bigger. Chloride is more stable, it's just happy sitting on the couch.
So it is fluorine then, right?
Sorry. I circled the one that's more, I circled the more stable one. The more basic one is the one that's less stable. It's like, okay, I need an H, because if I take an H, I'm going to go neutral. Then I'll really be happy, because neutral is best. Look at that. The most electronegative element on the periodic table is not as stable as an anion as the chlorine. There's a size. So electronegativity is not the be-all answer. Size is also important. F minus is actually a decent little base. It's not that strong, but sometimes used as a base. CO minus is never used as a base. Which is more basic?
Ammonia.
Okay, you memorize that in Gen Chem, right? Ammonia's a basic. But do you really know why?
Is
Do you?
that ammonia's sp3 and water's sp2, right? Would that be
Yeah,
wrong?
but they're different atoms, so let's start with just the difference, some other more simple difference. Oxygen's more electronegative. These are not anions, but still, here we got good parent, bad parent. Which is a better parent? Which holds on to its lone pairs tighter? Oxygen lone pairs. Nitrogen lone pair. Inherently, because nitrogen just doesn't hold on to them as tight. Oxygen more electronegative. Not really a hybridization effect. They both have the same hybridization. All those lone pairs over there are sp3. But there's a difference between an oxygen sp3 and a nitrogen sp3. Because oxygen inherently holds them tighter. It's an electronegativity effect. Not a hybridization effect, not a resonance effect. Which carbanion is more basic? I got a lot of sp3 carbon. Which one's more basic?
On the left.
Right, why?
Because all the CHs acting as dominant.
Yeah, inductive donation, making this even more electron rich. Okay? It's like if this was colored some type of red intensity, this is like red, this is like red, you know, like this commercial's like paint. Huge amount of electron density over there. Compared to this, because more electron density is going to make that more basic. So I got to have a proton. Both of these are very basic, very basic. Carbon being minus, it doesn't love it. But the one on the right is more basic. Okay, we used 4 arguments roughly there. They were numbered 1 through 4. We used them for acids. Because when we were looking at acids, we looked at the conjugate bases. And then with bases, we realize that high electron density makes it a better base. Or the electrons just out there more available makes it a better base. What are good bases? Neutral nitrogens tend to be good bases. First off, usually bases are anions. We said that. Minuses. That makes sense. Hydroxide, good base. It wants to go take an H and become neutral. Most bases are anions. But you can also have neutrals. And the most common neutral atom to be a base is a nitrogen. Can a neutral carbon be a base? Well, a neutral carbon doesn't have a lone pair. Unless you look at a unique case, right? There's a neutral, look at those carbons up there. Do any of those neutral carbons have a lone pair? No. Neutral carbon's not going to be a base because it doesn't have a lone pair. But nitrogen does have a lone pair. And it's the least electronegative of the ones that have lone pairs, and so it doesn't hold them as tight. The lone pair's out there. Neutral nitrogen, good base. Hybridization though, what type of nitrogen lone pair is the best base? sp3. And sp3 nitrogen is a good base. And sp2 nitrogen, which is held a little tighter, not quite as good. Sometimes nitrogen compounds are called nature's bases because neutral compounds are more likely to occur in nature. But all of these here are natural products that contain a basic nitrogen. And these, because they contain basic nitrogens, are called alkaloids. What does that term mean? What's a humanoid?
Human-like
Human-like?
thing.
What's an alkaloid?
Alkaline.
Alkaline-like. And what does alkaline mean?
Basic.
Basic. Okay? They're basic-like. Now this is probably compared to something like hydroxide. They're not as strong as hydroxide, but they're alkaline-like. They're called alkaloids. That term's been around for 200 or 300 years. And young organic students should know what an alkaloid is. And maybe you could refer to this in biology. Okay? Many beautiful alkaloids out there. Some of these you've heard of. Ergoline. It's an ergot alkaloid. Found in some mushrooms. You got any mushrooms growing in your yard? Been a lot of rain lately. Okay? I bet they got some ergot alkaloids in them. Compounds like this. Which nitrogen is basic? One's basic and one's not. That's in a p orbital. This is in what? sp3. There's your basic nitrogen. Lone pair and p orbital, not basic. Every one of these contains at least one basic nitrogen. LSD. Anybody familiar with LSD? More around in the 60s and 70s. It's an alkaloid. It's a natural product that contains a basic nitrogen. It's got 3 nitrogens, but only one of them is basic.
The bottom. No, not the bottom.
Which one's basic?
The middle one.
Not the middle one.
Middle one's basic. The other 2 are not. Anybody like any of the other alkaloids? You know any of these? Cocaine, that is actually an alkaloid, yeah. Quinine? Original anti-malarial drug? Nicotine, etc. Morphine, very important compound. Okay, alkaloids. All right. When I was in 3rd grade, we used to do at the beginning of class, like we used to do finger exercises. Get ready for the day. We go. We go up and down, up and down. I don't know why we would do this, but the teacher would have us do this. Usually this finger exercise, finger exercise. I don't know why it was what it did. Or probably just gave us something to do and look at the teaching. Finger exercise. You might need doing finger exercises. Miss Henderson. Miss Henderson. She's pretty young out there. Probably about 30 years old. Remember one time I sat near the wall or something. There's a vent that didn't have a cover on it. I crawled. I threw a paper airplane into it, and she got a little mad.
At least you weren't that kid put like a snake on the side of
Okay, let's look at predicting equilibrium of acid-base reactions. Reaction will favor the side of the weakest acid. Now, I know you know all this from Gen Chem 2, because in Gen Chem 2 you do all your acid-base equilibrium, right? I think so. So you should know all this. Reaction will favor the side with the weakest acid, right? For example, look at this reaction. This acting as base, take a proton from water, we make methane plus hydroxide. You need to know the strength of your acids. pKa's are given here. In other cases, maybe you have to determine relative acid strength. Okay, what's the acid on this side? Water. Water has the proton. What's the acid over here? What has the proton now? Basically, if we could, the proton that's being bounced back and forth, if it was in red, one of these would be red, and now one of those would be red, because the proton now sits there. This is the acid here, that's the acid here. This is 16, that's about 40. Which side's favored? The weakest acid. Which is the weaker acid, water or methane? Methane. So this side's favored. The acid's in equilibrium. That side's favored in the equilibrium. By how much? Difference in your pKa's. What's the difference? 10 to the 24. What is that? That's got to be at least 100 gazillion. So at equilibrium, you got 100 gazillion of these and one of these. Turn that into a percentage. It's probably going to be 99.999999999% there, and then the other is, I would call that complete. No? It's complete. This is going to completely react here, and you're going to make methane and form hydroxide. We can assess the pKa's and basic understanding. Down here, acetic acid. You put it in water. We can have an acid-base reaction. Well, that's an acid, so probably it's going to serve as an acid. Water can act as a base, take an H. Water takes an H, it becomes hydronium ion, and we leave behind the conjugate base of the acid. The acid over here is 5. The acid over here is the hydronium ion. It is less than 0. Which side is favored? The weaker acid. Over here, this side's favored. So if you put acetic acid in water, does it completely form the anion? No, it only partially forms the anion. Most of it stays like this. And that's pretty much the definition of a weak acid. It doesn't completely ionize. It predominantly stays like this. But some of it does ionize. It forms some proton in the equilibrium, some acid, some ionization. All right? Well, we see that in our numbers. Which side's favored? This side. By how much? Difference in here. depending on what that is, it's 10 to the 5. So 10 to the 5 is what? That's 100,000, isn't it? So at equilibrium, you got 100,000 of these, and only one of them is ionized. Question?
I have a question about drawing the reaction error, so if it's, at what point should we draw just like the forward error to like indicate that it goes essentially to completion?
That's a great question, yes. If I had drawn this just, out on a Friday night or something, drawing this reaction, I probably wouldn't even have shown the equilibrium, because it ain't. In theory, yes, everything's in equilibrium almost, but in practice, it ain't in equilibrium. It's way to this one, right? You're not going to be wrong. I probably would not draw it as an equilibrium. Down here I would, because it's more of a true equilibrium. Okay, let's see how we can do these. Do these on our own. Show the result. Okay. Show the products. And then tell which side is favored, and then by how much. Just like we did up here. For those here. I'll do the first one for us, and then you can work on those. And we'll probably look at them tomorrow. We'll move ahead to other stuff. Let's do the first one. Okay? Now, I could give you one where I don't even give you a PK at all. And you should still be able to deal with it. You may not know precise numbers, although you can look them up. You don't really need precise numbers. You can still say that, okay, just general relative stability, I think this side is going to be favored. All right? So, how can we assess this? It's an acid-base reaction. The handout is called acid-base. All right? Until we start doing other reactions, we're doing acid-base. But even when we start doing other reactions, acid-base is always possible. So, what's the acid here? What's the base? Well, hydroxide is a common base. Could act as an acid, because it does have a proton. It's typically a base. I'm also giving you a pKa here, which refers to an acid, so maybe this is the acid. All right? Show the products. What have we done before that you need to do here? You need to identify the acid and the base. Beyond just that's the base, this is the acid. Yeah, this is the acid, but which H? CH or NH? See? We talked about that. You've got to do that. Yes, it's the base, but which atom? That's pretty easy. There's only one atom of the lone pair. What if the base had multiple atoms? Could you identify which was most basic? Like in those alkaloids? Okay? Anybody got products yet? You need all lone pairs. All lone pairs, both structures. Both structures? I can't see it. And the other structure? Right, both. All lone pairs. All lone pairs. Charges. Charges. All lone pairs. All lone pairs. Remember what I said, if you're going to show a charged atom, I want you to show all lone pairs. What's not good is to show only half of the lone pairs. Because that tells me that If you showed none, then I'm like, well, you gotta show, but you only showed half the lone pairs, I think. Good. Where's your charge at? You got it floating up there in space.
Oh,
Charge needs to
right.
be shown on the atom. And I think you're also missing lone pairs. If it's minus, you don't usually need to show the 1. Just a minus is fine. Let's look at these. Anybody else? All lone pairs, missing lone pairs. Good. Oh, you did a mechanism. Oh, yes, very helpful because it shows you exactly what's going on. Like you might use equations to do a math problem, right? Yeah. Absolutely. I would recommend it. Very good. In your mechanism, I would circle the lone pair. Show the lone pair in that conjugation. Check the mechanism we showed on the beginning. Yeah, actually, I wasn't looking at mechanism, but okay. Everybody should have a mechanism there. Okay? Your mechanism is how you get the answer. Now, maybe you're good enough to do it without a mechanism and just do it in your head, but I kind of doubted that this intro level. Everything you do, mechanism. Mechanism, you gotta know that you should be relying on your mechanism. Do you want to get the answer right the majority of the time, 100% of the time, or just kind of randomly? If you want to get it right 100% of the time, use and know your mechanism. Yes, you got it right. You didn't use your mechanism. Were you thinking mechanistically? I would practice showing your mechanism. Trust me. When we get to test 2, test 3, if you don't know how to do mechanisms, you're not going to be able to just pull answers out of the air, maybe like you're able to do right here. Okay, let's look at these. Yes, this is the base, this is the acid. Which is more acidic? CH, would you rather make an anion on carbon or nitrogen? Yeah, most acidic. Okay, we talked about how to determine that. You got to do that before you do any reaction. Now our mechanism, it was on that single page. It showed the generic mechanism. It's the same always. A lone pair of the base does what? Takes the H. These electrons move on to nitrogen. But the nitrogen had one lone pair to begin with. And when this moves on to the nitrogen now has 2 lone pairs. And so we got nitrogen, carbonyl, this is succinimide. How many lone pairs on the nitrogen?
2.
2. And that's a minus charge. Plus what?
Water.
Water. We can show it out of full structure. 2 lone pairs. Because the other lone pair bonded to an H. Charges. Neutral went to minus. Minus went to neutral. Here we go. pKa of this is 8. What's the pKa of the acid over there? 16. You need to know water. 16. Which side's favored? 8 or 16? Weaker acid's favored. This side's favored. By how much? By 10 to the 8. The difference in your pKa. And 10 to the 8, I believe, is 100. No, it's 10 to 9 would be a billion. 100 million? At equilibrium, you got 100 million of these and only one of these. Question, is hydroxide strong enough to deprotonate succinimide?
Looks like it.
Well, if you do the reaction, you're going to get 100 million of these to 1. That's like 99.9999999%. Thus, again, is hydroxide strong enough to remove the proton? Yeah. So sometimes we may have to determine what type of base do we need to do the job. Hydroxide will do the job. What if we used a base and the equilibrium lied way over here and like this? That means the base didn't do anything to this. That'd be not a good base. Hydroxide does. It fully deprotonates it. It takes it this way completely. Yes, the equilibrium is like this. You see that the other way here? It's even smaller than that. Yes, that reaction is going to take place. Okay, there's others to do down here. I want you to look at those on your own so you can see what type of questions you have instead of me just telling you the answer. What about pH? How will an acid or base exist at a certain pH? This can be determined using the Henderson-Hasselbalch equation. Did you guys look at this equation in Gen Chem?
Yes.
Yes.
Yes? Okay. I don't know exactly what you do with it. You'll look at it in biochemistry as well. It says that pH equals pKa plus log of the basic species over the acidic species. Okay? This is essentially your conjugate acid-base pair. You can look at this here. In summary, basically you have three different variables here, and if you know two of them, you can determine the other. All right? You know the pKa, and you know the pH, you'll be able to then determine the ratio of B to A in this map. In summary, if pH is greater than pKa, the basic species will predominate in your equilibrium. Because for pH to be greater than pKa, for example, if pH is 8 and pKa is 7, pH is greater than pKa, what does this have to equal? 1. Because 7 plus 1 would be 8. Well, the only way this is going to equal 1 is for B to be greater than A. Okay? That's where this comes from. Now, on the other hand, if we reverse this, if pH is less than pKa, A will have to be larger. All right? That just comes from the math, but that's a summary statement. Acetic acid. How will it exist at pH of 7, which is blood pH? How will it exist? First off, you got to know what equilibrium we're talking about. This is an acid. All right? It can exist ionized. Now, this is a simplistic ionization. We can include water. Just reacting with water, and instead of making this, we make hydronium ion, where water acts as a base and takes the H. We showed that above. A lot of times we just sort of leave the base out and show it more generic. And actually that can be confusing to beginning students. But it's this sort of convention of sometimes things are overly simplified. All right? But that's just ionization. But what we do show here is the two forms. The neutral form and then the ionized form. The acid and the conjugate base. This is the two form. This is the acidic species because it contains the H. This would be the basic species because it does not contain the H. Which will predominate, A or B, at pH of 7? What do we need to know here? We need to know the other variable. pKa. What is the pKa of acetic acid? About 4. Or do I say it's somewhere else?
Yes, it's 5.
Where is that?
Right under where it says A.
To your left.
Okay, all right. It's about 4 to 5. Let's go with 5 since I wrote that there. Okay. So what's Which one's going to be favored? Well, let's look at this. If pH is greater, we got to compare the pH to the pKa. And you got to be careful that you don't get it backwards in your comparison. One of these is a constant. The pKa is a constant. Never going to change for that acid. The pH is variable. You can change pH readily. What you want to look at is the thing that can vary, how does it compare to the constant? For example, is it on the high side or low side of the constant? 7 is on the high side of the constant. Now, high should mean to you basic. High pH, basic. High side, basic. It's on the basic side of the constant. Thus, the basic side is going to predominate. Now, if we look up here, we can see it here. The pH is greater than the pKa, right? Yeah? So B will predominate. But I'm explaining it just a little bit different way. I'm telling you that the pH is on the basic side, it's on the high side of the constant. So that tells us that the basic will predominate. So at pH of 7, how will acetic acid exist? It mainly exists like that, in the ionized basic form. What's the ratio of the two at pH of 7? What percent is ionized? What's the ratio of these at pH of 7? It's a difference in your pKa's. Difference of 2. Well, that's a pKa. It's a difference in these logs here. Difference of 2. And 2 is what? 100. It's 100 to 1 at pH of 7. The basic form predominates. It's 101. What if pH was 8? Basic form would still predominate, and it would be what ratio? 1,001. What if the pH was 6? And the basic form would still predominate, it would be 10 to 1. What if the pH was 5? What if the pH was 5? It would be 1 to 1. Because if the pH is 5, if both of them are 5, what does this have to equal? 0. That means that this is 1 over 1. You see? When these are equal, when those are equal, B and A are equal. Okay, that's the math. Take a look. Note down there. Oh yes, the miscellaneous points to remember. Again, free information. No extra charge for this. Let's look at this here. Anytime you see things written here, question marks, these are questions for you to be thinking about. We may or may not ever go over them, but stop by. Okay, always want to be testing yourself. Over here, most drugs are given as salts, ions, ion pairs. Codeine is actually an alkaloid, pain medication. It has a hydrochloride salt. Reacted with HCl. These electrons take the H, these move to here. This mechanism gives you a nitrogen H bond. The nitrogen is now positive. And what else did we produce? Cl minus with four lone pairs. Here's the product. Okay, coming this way. Which side's favored? We need to know pKa's. What's the acid here? HCl. What's the acid here? This thing. It's got the H now. It's 8.2. I have to tell you that. You're never going to learn. Well, kind of. It's a tertiary sp3 nitrogen. The conjugate acid has a pK. I would say about 10. I'd be a little bit off in this case. That is in the table in the lab manual. Okay. Which side's favored? -5 or 8? Weaker acid, 8. How much is this favored by?
10 to the 13.
10 to the 13, 100 gazillion. If it is this reacts with HCl, you're going to make this. It's kind of intuitive because we're reacting with strong acid. I mean, it's going to give you something. But it's all in the numbers. And then this is how the drug can be existed, isolated like this in the salt form. Drugs are given as salts because it makes them more soluble in water. Most of us are aqueous based, right? So you want your drug to dissolve. Get that big organic compound with lots of hydrocarbon to dissolve in your aqueous blood. It'd be best to have some ionic portion to it. More ionic, more towards soluble in water. Is it actually soluble in water? I don't know, but it's more soluble in the neutral form. Question?
For this one, without being given the pKa's, you could go ahead and tell which one would be favored, knowing that HCl is a strong acid, right?
Pretty much, yeah. Strong acid meaning it's going to have like a negative here. There's some idea that you're right. There's some idea of this that which is a stronger acid, HCl or disco? Well, in Gen Chem you learned this is a strong acid. Did you learn that that was a strong acid? The reason why is because it ain't. So you know that's going to be the stronger acid. It's going to have a lower pKa. So you know how much is favored just by that. Now what the difference is you may not know because you don't know if this is 2 or 8 or 20. But you do know that this should be favored. Okay, there's questions in here throughout. There's another acid-base question over here. Let's see what type of questions come up with that. Okay, the next handout will be alkanes, blue handout. And the one I gave you today, which is purple, are they extra purples? Oh, I got one. Is it purple? The purple is sort of an outline, and then the blue is sort of a handout. Kind of go together. Although the purple does have some, we'll be doing some work on the purple. But it is sort of the outline. And we're moving into alkanes. We're going to take a closer look at those compounds as a group. Including nomenclature, how to name alkanes, that's covered by video only. Okay, I sent you this, one of these blue ones by email. To get it to you as early as possible there. We'll see what type of questions come up with the nomenclature maybe tomorrow. You're also watching IR by video. We'll see what type of questions come up there tomorrow. With the alkanes, we'll see some more stereochemistry, variety of things. One of the two big things with the alkanes is conformations, rotations of alkanes. Okay? Sigma bonds can rotate. What do we need to know about the potential for rotation? How to draw certain rotations on the board. We also have rings, cyclohexanes in particular, ring conformations, how they can sort of, we don't really say rotate, because you can't do this, but you can sort of move them, call it different conformations of the ring. All right, please be doing some reading about this type of stuff. You see the topics in the handouts. As we finish up, I want to go back to, I think, the physical properties handout. It was pink. Any questions about that handout? We just talked about drugs. This is near the back. So if we can get the drug to become ionic, be more soluble in water, and most drugs are given as ionic. But not all of them. Ever heard of Prilosec? What is it called? Prilosec OT something? Is it over the counter? Is it over the counter there? Yeah, mainly because it's off patent. And you ever heard of Nexium? Or is Nexium a prescription?
I think you can get it over the.
There's a different grade for
Yeah, they have a
prescription.
legal claim for over the counter and then.
Okay, for that one? Well, guess what? They're both the same. Right? This is the structures. This is Prilosec. It's all neutral. This is Nexium. What's the difference?
Yeah.
The nitrogen anion. The H has been removed. The conjugate basis here. Nitrogen anion. How many lone pairs on the nitrogen?
2.
2. You see, they don't like to show lone pairs. It's clear. They're like, we're not going to do it. All right. Which drug should be more soluble in water? The anion, right? It's got this ionic portion. By the way, what's the spectator ion or the counter ion, cation? If it was sodium, you would just have one of these and one sodium. But it's magnesium for some reason. And since this is 2+, you got to have 2 of these for every magnesium. So that's why that's in brackets. Okay. Just like if you had magnesium chloride, right? If you had magnesium chloride, you would have 2 chlorines, 2 anions. Well, the anion is this, 2 of these. This is his compound number. There's 2. Okay. It should be more. It's ionic, more soluble in water. It's the same thing, though. For example, if you take this and it goes to the stomach, what's in the stomach?
Hydrochloric acid.
HCl? What's HCl going to do to this anion here? That's an anion. It's going to want to take an H. It reacts with HCl and becomes what?
Prilosec.
Becomes this. Plus magnesium chloride. All right, there you go. So if you're going to put this in the stomach, you might as well put that in the stomach. They came out with this, and then when the patent went away, then they came out with this, and they got a new patent. Probably because, yes, it becomes the same thing. But this might be faster because this reacting in the stomach yes, it does give that. Where this, when it goes into the stomach as a solid, it's going to take a little time to dissolve. A little bit of, okay. where this immediately dissolves a little faster. But as soon as it dissolves, it becomes that. It's just it may dissolve a little faster because it went in as an anion. So maybe that's how they were able to get a patent. Maybe they said that the onset of action was a little bit quicker for the anion. But once it's in the blood, it's the same thing, right? You see that? It's chemistry. And then you could say, well, which side's favored? Well, this side's favored because it's a strong acid. The other one's going to be weaker, and the weaker acid's favored. All right. Let's see here. Agricultural, please take a look at that. This one on the back, I've got the, please take a look at that. I got the colored copy here. This is interesting a little bit. Just solubility. Compound at the top, R groups, okay, generic, they have to be defined somewhere else, defined below. If both R groups are methyls, it's called methyl red. Because in the solid form, that compound's red, but when you dissolve it, it's yellow. And these are methyls, and you got two layers, cyclohexane and water, because they don't mix. The compound actually refers to water layer. We can tell by the color. Now, that's a little bit odd because it's an organic molecule that's neutral. Is it really? That could be a good discussion. Is this really neutral? You've got an acid and a base. We might talk about that. This could be ionic, even though it's shown like this. But if the R groups are made bigger, ethyls, it starts preferring the cyclohexane. And propyls, it really prefers. Does that make sense? These R groups become more hydrocarbon. It's going to prefer the organic more and more. All right? To me, that's a nice illustration. There's questions you could ask here, but as the hydrocarbon content increased, it prefers the organic solid more and more and more. I'm interested in what type of questions you have about that. What may be a little bit confusing, because I potentially see it and I would like for you to maybe ask. And then there's other applications down below. Lots of applications. That's the fun stuff. That's where we're here, but we don't have time to talk about every single application. Hopefully you're looking at them and you've got some curiosity. Okay. See some of you this afternoon. Yes.
There was a question about the
Ask me on the way out. We're pretty much need to get out.